right, recording started. Sorry about that. All right, so let's talk about classifiers and decisions. Yesterday we talked about how classifiers output 0 or 1, or one of a certain number of classes. And in logistic regression, the model makes a prediction about a probability, right? It makes a numeric prediction between 0 and 1. And so what we do is we say that the decision rule for the classifier is how we convert from the probability to a class. So most commonly what we do is we say that if my classifier gives a probability that's 1/2 or bigger, then we'll predict 1. And if our classifier gives a probability that's lower than 1/2, then we'll say that this particular point is labeled as 0. Okay, so in other words, if we think that it's more likely that y is 1, then we'll label 1. And if we think that it's more likely than not that y is 1, or y is 0, then we'll label 0. Okay, so this is the simplest and the most common classification rule. And this is also equivalent to this formula here. Okay, so the reason why these two things are equivalent is because if you remember the sigmoid function from yesterday, the sigmoid function goes from low to high, and it crosses the 0.5 mark when theta.x is equal to 0. And so anything to the right of 0 will be labeled a 1, and anything to the left of 0 will be labeled a 0. Okay. So if you see either one of these, you should know that these two are equivalent. Sometimes we'll write this just because they're shorter. Now you don't have to set 1/2 as this cutoff. And in fact, in a lot of real-world cases, you won't use 1/2 as your decision rule cutoff. The reason why you won't choose 1/2 is because by adjusting your cutoff, you can avoid certain types of errors. All right? For example, if you set your decision rule cutoff higher than 1/2, what you're saying is, I want to make it harder to label a point as 1, which means that you're going to get fewer false positives. Usually, setting the appropriate decision rule depends on the domain. So, for example, if you're very concerned about making an accurate prediction, like a yes or no, if your probability is too close to 0.5, your classifier can also report, I can't decide, or I can't label this point because I'm not sure about my decision. So this comes up a lot in various domains. For example, in email spam classification, we're okay with a little bit of spam getting into our inbox, but we really don't want an important email getting sent to spam. In medicine, we're okay with sometimes having a test give back a false positive, but we really don't want to miss a case where a medical scan says you don't have a disease when you do have a disease. So it really just depends on the domain of interest, and what you should do when you're considering the cutoff is think about what types of errors will be worse than others. Okay. And to evaluate how good a classifier is, I need to give you some more vocab. All right. So here I have a table, and oftentimes what we do with classifiers is we say, okay, we'll compare what the classifier predicts with the true labels. Okay, so for example, in this box here, the classifier predicted 1, and the true label was also 1. In this bottom right box, the classifier predicted 0, and the true label was 0. And here we have a false positive, and here we have a false negative. The way I remember this is the first word here, true or false, refers to the truth. The second word here refers to my prediction. Okay. Now the most common metrics that you'll see are accuracy and the error rate, which essentially says what proportion of points did I classify correctly. It's the most obvious one, and the one that scikit-learn uses by default, and the one that we've been using by default so far. But in reality, accuracy and error rate are perhaps not the ones you want to use, especially when you have unbalanced class distributions, which means you have a lot more of one class than the other. Okay? And in those cases, we want to use different metrics, and here are two more metrics that we'll use, which are called precision and recall. Okay, so the way you read these formulas is you say, okay, to calculate precision, I look for TP, and divide by TP plus FP. That's one way to remember it. But the better way to remember it is to say, okay, what does precision kind of mean to me? Precision means to me, if my classifier says 1, how precise are its predictions, which means of the ones that my classifier said was 1, how many were actually 1? For recall, the way I remember recall is saying, okay, well, if my classifier, how many of the true ones does my classifier recall as 1? So it makes sense to me, but it might not make sense to you, that particular wording. And what you should do is try to think about what we're calculating here for precision and recall, and try to come up with a statement that makes the most sense to you to help yourself remember what's going on here. All right, so accuracy and error rate are the most obvious and common, and precision and recall are used when we have rare outcomes. So for example, if only 5% of emails are spam, then accuracy is not so good, and we'll see why on the next slide. Okay, so we're going to go over a bunch of these metrics, and I think what you should do is not try to memorize all the metrics and how to calculate them, but what you should do is try to remember what they're useful for, okay? And you should try to remember intuitively what they mean, so you can just get a grasp on the meaning of calculating these. Okay, so accuracy I remember as just the proportion correct. Error is the proportion incorrect, or 1 minus the accuracy. The precision I remember as of the predicted ones, what proportion was actually 1, or how precise are my predictions. For recall, I remember it as of the actual ones, how many were predicted 1, which essentially is how many examples did my classifier recall correctly as 1. Okay. All right, so I want to talk to you about why we don't like using accuracy alone in a lot of cases. So if we have 100 emails and only 5 of them are spam, what is the accuracy of a classifier that only predicts not spam? Okay, so if we assume that spam is labeled 1, then this classifier only predicts 0. So please think about it. And then think about what is the precision and recall of such a classifier. Okay, so if you have a guess, turn to your neighbor and see if you guys agree on your statements here. So accuracy, precision, and recall of a classifier that only predicts not spam. Go ahead. All right, so a little warm-up question. So the accuracy of this classifier is 95% accurate, right? It's 0.95 because there were 95 emails that were not spam, or ham as we like to call it, and 5 of them were spam. Okay, so 95 emails were ham, 5 of them were spam. If my classifier only predicts 0, then it will be right on 95 out of 100 emails, which gives us an accuracy of 95%. The precision of this classifier and the recall of this classifier are both 0, right? Because there is no case where a classifier predicts 1. And for both precision and recall, we have true positives over false positives or false negatives. Okay. And so if you looked at accuracy alone, you might think that this not spam classifier is doing really well, right? It gets 95% correct. But in reality, it's not doing anything particularly meaningful. It's just predicting not spam for every single example. And the only reason why it seems to have a high accuracy is because we have a lot of ham emails and very few spam emails. And that's generally true when you have like some labels that are very infrequently encountered compared to others. Okay, so because of this, we don't like using accuracy alone. And what I'll do is I'll show you another metric that we prefer called the area under the curve metric. You may also hear of the F1 score metric. Okay, so basically we're going to like talk about metrics and then we're going to combine metrics, so it'll be like metrics on top of metrics. But what you should take away from this is that you have some basic calculations based on this table here. And usually in real life, we'll combine some of these metrics to get an overall score for a classifier. Okay, so the F1 score is like a geometric average of the precision and recall. So if you see F1 score as a classifier evaluation metric, you should think to yourself, okay, it's combining precision and recall in some way. Okay. So what I like to do for these is I like to draw what are called confusion matrices, where I essentially take a classifier and fill in this table with how many examples the classifier puts in each box. Okay, so for example, here is a classifier, here's a confusion matrix for a classifier from yesterday, where we talked about predicting whether a team wins an NBA game from their field goal percentage difference. And we see here that the classifier is pretty good, and it does false negatives and false positives at about an even rate. Okay, so for example, if there is 0 in this box here, I would say something like, it's very good at detecting when teams lose, but not very good at detecting when teams win. Okay. And you should be careful. For today's demos, I'm always going to put 1s in the top left and 0s in the bottom right. But scikit-learn's confusion matrix function gives it to you in the opposite order. So it'll put 0 on the left and 1s on the right. So you should just be very careful when you're reading documentation what like confusion matrix function is putting, like where each box is getting placed when you call confusion matrix functions. Okay, so let me show you what this looks like. Okay, so we have here the data frame from yesterday, which contains the games in the NBA and the field goal percentage difference, as well as whether the team won or not. All right. What I can do here is, just to save time, I'm just going to import the logistic regression model from scikit-learn, like so. And I can define my X matrices as I have before. So here is field goal percentage difference, and here is the won column. I can define a model. Let's call this logistic regression. So logistic regression in scikit-learn comes by default with regularization. But just for consistency with yesterday's lecture, I'm going to turn off regularization, so this is a penalty of none. And if I want to set this penalty, I need to say the solver is a different solver than the default. And so the default solver uses what's called like a second-order gradient descent algorithm. In other words, it doesn't work. If you try to do it with the default solver, it'll complain. So usually what we do is we try to run it with the defaults. If it doesn't work out, we'll try to switch to a different solver. And the solver just means it uses different variants of gradient descent, more or less. Okay, so this particular variant of gradient descent is called SAGA. It stands for stochastic average gradient. But unfortunately, the authors of this paper who made SAGA didn't say what the last A stands for, so we don't actually know what the A stands for. In any case, we can fit the model. And here's the model. Oops. All right, let's try that. Okay, so we have a model, and I have here a function that makes a confusion matrix, or plots the confusion matrix. And to make the confusion matrix, what I need to do is take my classifier, get its predictions on the training set, and I can save this in ypred. And then what I can do is make an array. Here's my array. In the top left corner, I want the sum. The sum of when my predictions are equal to 1 and the actual values are equal to 1. So this is the top right corner of my confusion matrix box. Okay? And I can just copy and paste this in the 4 cells here. Change this to a 0. Here's 0. Change this to a 0. And here's my confusion matrix, roughly speaking. Okay, so just 4 numbers here. The same 4 numbers that I had on my slide. It's not pretty, so we can make it pretty. I can save this into a variable and then call plot confusion on this variable. So same confusion matrix as the slide. Okay. So doing this is a little nicer than just asking for the score. So scikit-learn comes with a built-in score function. And if I call score on x and y, it'll give me just the raw accuracy, right? So it's the top left box plus the bottom right box divided by the total number of points. The score gives me the accuracy, but usually what I'm more interested in with classifiers is this confusion matrix right here, because it just gives me more information. It tells me what kinds of errors my model is making, as well as how well my model does overall. Okay. Any questions about this so far? Okie dokes. Why don't you try it out? So here are 2 classifiers, and I've plotted the confusion matrices for each one. Please compute the accuracy, the precision, and the recall for all 3. Okay, so the accuracy for the first model, if you take a look at this confusion matrix is actually the same one for the emails and like the spam example that I had on 2 slides ago, right? So we have 95 emails, or 100 emails, 95 of them are ham, and 5 of them are spam. And here I have a classifier that only predicts not spam, 0. And so it'll predict these 95 emails correctly, but predict these 5 emails incorrectly. And we said before that the accuracy is 95%, so 0.95. And the precision and recall are both 0. Okay, so we have your 0.95, 0 undefined, because you're doing like 0 divided by 0, which is not technically defined, but we'll call it 0 for now. And recall is 0, because you have 0 over 5. Okay, so for the classifier on the right, we have 100 examples, and of those 100 examples, the classifier marked 80 of them correctly, so we have an accuracy of 0.8. Precision is 50 over 70, the top row, and recall is 50 over 50, the first column. Okay, how would you interpret these confusion matrices? So if I saw this confusion matrix, I would say, okay, my classifier, if I actually fit a classifier and I got this confusion matrix, which will probably happen to you in real life, you'll probably say something like, okay, well, my classifier here is just super conservative. It never predicts 1, it only predicts 0, and it's only getting a high accuracy because I'm using accuracy as my metric of choice. Okay? The classifier on the right here, I would say, is really good when the true label was 1, but it's pretty bad when the true label is 0. Okay, so simple conclusions, and if I had real data here, I could tie these back to some actual predictions on the actual data. Okay. So I have here 2 more metrics, all right? So the false, that's supposed to show up one at a time, but here we go. We have false positives and true positives, and the false positive rate is this column here. It's the false positives over this column here, and the true positives is the true positive box here over the first column here. Okay, and the way you interpret the false positive rate and the true positive rate is you look at the truth, and you look at how many of the truth you marked as 1. So the false positive rate here is, of the ones that were zeros, how many did I mark as 1? And the true positive rate is, of the ones that were 1, how many did I mark as 1? Which turns out to be the same as recall. Okay, so true positive rate is the same as recall. False positive rate is slightly different. Okay, so here we go. We have like 6 different metrics. And sadly, it's just a state of the world that you have a ton of different metrics for evaluating classifiers. You kind of care about all of them, but you kind of don't, in the sense that you want all of them to be like as high as possible, or for true positive rates, for example, you want those to be as high as possible, and you want the false positive rate to be as low as possible. But in real life, what we'll do is we'll say that 6 metrics is way too many. We'll try to combine them and get a metric that we'll use just in general. And that's what we'll do right now. It turns out that there are even more metrics that essentially involve different combinations of these boxes. You may hear about specificity and sensitivity. Those are yet another pair of boxes that we're doing like divisions over. Okay. The reason why I introduced false positive rate and true positive rate is because it turns out that if you change your decision rule, okay, so if our original decision rule was 1/2. Anything above 1/2 will label 1, anything below 1/2 will label as 0. And if you change that decision rule, you change the false positive rate and the true positive rate. Okay. So, for example, if you set your decision rule cutoff to be 0, that means that you're going to label all your points as 1. Because the decision rule is anything above this point here, I'm going to label as 1, and anything below I'm going to label as 0. So if I set my cutoff to be 0, all my points will be labeled 1. If I set my decision rule cutoff to be 1, all my points will be labeled 0. Okay. So for both of these 2 cases, please find the false positive rate and the true positive rate. Okay, so if I label all the points as 1, then in my confusion matrix, I'm going to have some positive numbers on the top row, but only zeros in the bottom row. If I have that, then the false positive rate and the true positive rate are both 1, because I have some positive number divided by false positive plus 0, which means we have false positives over false positives, which is equal to 1. And the same thing here for the true positive rate. Okay, so how do we interpret that? We interpret this by saying, if I label all the points 1, then for the true positives, I'm doing really well, right? I'm labeling all the original 1s as a 1, good job. But I'm also labeling all the zeros as a 1, that's a bad job. Okay, so that's not good. If I label all the points 0, then the top row is 0, and the bottom row has positive numbers. And in that case, both the false positive rate and the true positive rate will be equal to 0. Okay. So it's good that we have no false positives, but it's bad that we have no true positives. Okay. And it turns out that if you adjust the decision rule cutoff between 0 and 1, you'll increase both the false positives and the true positives. Okay. And what you want to do is find the place at which you get the most true positives, but the fewest false positives. Okay. So the most good and the least bad. That's what we're looking for. There's a trade-off between the decision rule and false positives and true positives. And we can show that on what we call an ROC curve. ROC stands for like receiver operator characteristic, which is like a horrible name that like evolved from like radio transmissions. But for this class, you don't have to worry about the acronym. You just have to know that this is called the ROC curve. On the ROC curve, we'll plot the false positive rate on the x-axis and the true positive rate on the y-axis. And what we'll do is we'll draw this line, and we'll draw this line, or we'll draw this curve, by saying, okay, for every decision rule cutoff, what are my false positive and true positive rates? Okay, so we saw here that the x-axis here is a false positive rate, so this distance here is a false positive rate, which we want to be as small as possible. This height here of the curve is a true positive rate, and we want this to be as big as possible. Okay? This point here corresponds to the classifier that always predicts 0, because a classifier that always predicts 0 has no false positives and no true positives. So it goes from 0, 0 to 1, 1. Okay, and 1, 1 is a classifier that always predicts 1. And what we'll do for a classifier is say, we'll adjust the decision rule cutoff, and every time we adjust the decision rule cutoff, we get a different combination of false positives and true positives, and we'll just use that to draw this curve here. In real life, what you'll do is you'll draw the ROC curve on your test set, and then you'll say, okay, what am I happy with? Okay, am I happy with some number of false positives? If so, then I'll accept the fact that I can make some false positives if it lets me get some more true positives. Okay, yeah, question? Yeah, it's a good question. So the question was, I think roughly speaking, like you were saying, is the best choice of classifier like this point right here, which is like in the most top left corner? I would say it depends. Sometimes like usually for accuracy purposes, I think this is the best one, or sometimes it can be the best one. But if you care more about false positives and true positives, then you want to choose something lower on the curve. If you're okay with having more false positives, if it lets you get more true positives, then you'll choose a point higher on the curve. So it depends kind of on like your own, like in this situation, what amount of false positives are you okay with? Yeah. Okay, so let me show you how this works, and I'll have you draw one yourself. So I have here my model, which I fit on the NBA games dataset. And instead of predicting the classes for each game, I can predict the probabilities of winning. So here I asked scikit-learn to compute for me. The first column is a probability of seeing 0, which means a probability of losing. And the first column here is the probability of winning. So I can get out this first column by doing a slice, like so. Here's the first column. and I'm going to call this y hat. These are my model's predicted probabilities. Probability of y given x. Okay, here's y hat. Now I can import again this function that computes the ROC curve, and I can do the ROC curve here. I call it on y and y hat, like so. So it's relatively simple. And what it gives to me is the false positive rates, the true positive rates, and the thresholds, like so. And I can plot the false positive rates against the true positive rates, and here's my ROC curve. Okay. Now, I'd like to show you the ROC curve for a classifier that predicts at random. Okay, so this is a classifier that just says, I'll predict 1 or 0 at random, which essentially means that, let's say here, the random probs is equal to, we'll just take some probabilities uniformly at random between 0 and 1. Like so. Okay, so this just says, a classifier just doesn't look at anything related to the data, it just predicts some random probability between 0 and 1. So here's my random, here's like what we call a random model. And again, I can plot the ROC curve for this random model. Okay, so this is kind of like our baseline model. Any classifier that we fit on the data should definitely do better than the random model, right? Because the random model doesn't do anything sophisticated. Okay, so here is random props. What do you notice about this graph? It's a line with slope 1. So think about that for a little bit and why the slope is 1. To help you understand the ROC curve, what I'd like to do here is take a small data set and show you what I would do to draw the ROC curve. I'll make a table like so. And the idea behind the ROC curve is, right now my threshold is 1. If my threshold is 1, then I predict all zeros. So I have here y as my true labels, y hat as my model's predictions for these points, and pred, which is the label given to each point after I apply the threshold. Okay, so if my threshold is 1, my predictions are all 0. If I decrease my threshold, you'll notice that some points will become predicted 1. So right now these two are 1. And then now, if I keep going down, I'll have more and more points that I predict as 1. So here's another 1. And here's another 1. And then here's the last one. There we go. So I adjust the threshold, and it changes my model's predictions. And I also have here the false positive rate and the true positive rate at every threshold level, right? So as I decrease my threshold from 1 to 0, both false positives and true positives go up, but they go up at different rates. That's what the ROC curve shows. So again, going from 1 to 0, watch these two numbers now. So first true positives go up, and then false positives go up, and then let's see here, and then true positives go up, and then false positives go up. Okay, so to draw the ROC curve, what I'll do is in my mind, I'll slide the threshold down, and for every combination of false positive rate and true positive rates, I'll draw the curve. Okay? So why don't you try it out yourself? The ROC curve is a pretty tricky concept to understand, and the only real way to understand it is to actually do it with some toy data sets. And so take this data set here and try drawing the ROC curve based on just the y column and the y hat column. And you should apply the thresholds yourself and calculate the true positive rates and the false positive rates yourself. Let's try it out for a few minutes. Okay. So if you go through all that work, and you notice that it is quite a bit of work, you'll see that you get a plot that looks like this. Okay. So first, we start off with 0 false positives and 0 true positives. And then we decrease the threshold to let some predictions become 1. So we go up to 1/2 for the true positive rate, and then 1/3 for the false positive rate. And then now we're predicting all the 1s correctly, and here we're predicting all the 0s as 1s. Okay, so that's how you draw the ROC curve. And you should check at home and make sure you can get this curve out from these 5 points. Okay. Now, imagine with me a classifier that predicts every point correctly. Okay. If a classifier makes the right probability, like predicts every point exactly right, then what will happen is the ROC curve will go straight up and then straight to the right, which essentially means I can have if I encounter a curve that reaches the point 1, 1, this means that I can have no false positives and all true positives, which means that my classifier is doing perfectly on my data. And so because of this property, what we'll do is we'll define the metric called the area under the curve. And the area under the curve just says compute the area under the ROC curve. Okay, and the higher that area is, the better. And the reason why it's better is because the best classifier possible will have an area under the curve of 1. It will go straight up and then straight to the right. That's a rectangle from 0, 0 to 1, 1, which has an area of 1. This random classifier has an area of 1/2 because it goes through half of the square. Okay. So a random classifier will have a diagonal line through the plots. If you don't understand that, what you should do is try to take the notebook and do the random classification yourself, and then talk to me or your TAs and try to wrap your mind around this. And what we'll say is that we'll define the area under the curve metric as a metric that combines both the false positive rate and the false negative rate. And the random model has an area under the curve of 0.5, so any model that you make to your data should definitely do better than 0.5. It should get between 0.5 and 1. If you're getting less than 0.5, you're doing something quite wrong, or you probably have a bug in your code. And if you're not doing much better than 0.5, then you're not doing much better than randomly picking the labels. All right. Any questions on this? Yeah, Danny?
Why do we want the false positive rate to be 1 in this case? Because if you want the area to be 1, that would mean that the false positive rate, it would have to be a rectangle.
Why do I want the question was, why do I want the false positive rate to be 1? What I'm saying here is that the perfect classifier will get a false positive rate of 0 and a true positive rate of 1. And that means that it does everything exactly right. Nice haircut, by the way. Okay. Take a break. And we'll come back in 2 minutes. And the forum is open. Go for it. All right. Is anyone still filling out attendance? If not, I'm going to close the form in 3, 2. Oh, my mic is on. All right. Is anyone filling out attendance still? If not, I'm closing the form in 3, 2, 1. All right, it's closed. Okay. What we'll do now is we'll talk about gradient descent for logistic regression. And what I'll do is outline for you the steps needed to derive the gradient descent update rule for logistic regression. I won't go through all the steps today, but I'll give you the high level, I'll give you like the rough skeleton of it. And what you should do is try to fill in the details yourself and practice that derivation until it becomes second nature to you, just as how you should practice the other derivations for gradient descent update rules until they become second nature to you. And the reason why you should practice them is not so that you can memorize them. The reason why you should practice them is so you become familiar with the little mathematical tricks that we'll use to make that gradient descent rule look the way it does. Okay? And so you will likely not have to do the exact same derivation on a test, but you will have to know the skills needed to perform that derivation, which include like using the gradient, using the chain rule, simplifying the gradient if you have a gradient of like a vector, so on and so forth. Okay, so there are some skills here that are illustrated in this derivation that I want you to take home. Okay, so if you want to derive the stochastic gradient descent rule for logistic regression, the first thing we should do is compute the gradient of the sigmoid function because we'll need it later on down the road. Okay, so the sigmoid function, sigma t, is 1 over 1 plus e to the power of negative t. And so I'd like you to try out this gradient here, which is the gradient with respect to t of sigma t. All right, so go ahead and try it out. All right, so to do this gradient, you have to do the division rule, if you remember that. Or what I like to do with these gradients is I like to say this is equal to 1 plus e to the negative t. I wrap that whole thing in parentheses and take that to the power of negative 1. Right? So this is equivalent to the expression 1 plus xt to the power of negative 1. And that lets me do like the normal polynomial derivative rule. Okay, so if you do that step, you'll do the chain rule. You'll take the derivative of the polynomial, take the chain rule of the inside, and take the chain rule for negative t, and you'll get out exponent of negative t over 1 plus exponent of negative t to the second power. Okay. Now, here's something neat that we can do. We can simplify this expression to this expression. Okay. And what I did here was you can do it two ways. One way is to kind of split out this fraction into two fractions, and then notice that each fraction is looks pretty close to the original sigmoid function. Or you can work backwards. I can just claim this is true, and then you can plug in sigma of t into these components of this expression here. And if you simplify the expression, you'll get back this expression here. Okay, but these two things are equivalent. And it turns out that the gradient of the sigmoid can be expressed in terms of the sigmoid itself. Okay, so we have an expression here that just so happens to be conveniently enough expressible in terms of the sigmoid function originally. Okay, so what I'll do is if you see me write gradient of sigmoid, I'm going to write this and not the one above because this one is simpler. Okay, so it's pretty neat. If you try to be able to do this yourself, and again, I'm skipping the intermediate steps of this gradient here since we've done a lot of gradients so far. Okay, so here is the gradient of the sigmoid. And now what we have to do is say we want the gradient of the sigmoid after we plug in x sub I dot theta with respect to theta. Okay. So I'm going to define sigma sub I as the sigmoid of x sub I dot theta. And we want the gradient of sigma of I with respect to theta. It looks like this. And the reason why it looks like this is because the formula for the gradient of the sigmoid is the one above. So this is the part that looks similar to the part above. And the right-hand side, the last multiplied by x sub I, comes out because of the chain rule. Okay, so what we do for the sigmoid function is we treat x dot theta as if it was just a single variable. So we have sigma sub I times 1 minus sigma sub I. And then we apply the chain rule to the stuff inside this parentheses here. And it turns out that the gradient of x dot theta with respect to theta is x. So that comes from a previous lecture. But if you want to prove it yourself, you can. Okay. So we have here the gradient with respect to theta of x dot theta is x sub I. Okay. Now we have the little l cross entropy loss. And sorry for this typo. There shouldn't be a gradient here. This is just the loss for a single point. Okay. The loss for a single point is a cross entropy loss, so it looks like negative y sub I times log of sigma minus 1 minus y times log of 1 minus sigma. To compute the gradient of this loss, what I'll do is I will apply the chain rule once again. Okay, so the derivative of a log is 1 over whatever's inside the log times the chain rule applied to the gradient, the stuff inside the log. Okay, so when I take the gradient of the loss, I have 1 over sigma sub I times the chain rule, the gradient of sigma sub I. A similar thing happens on the second term, so we move the 1 over sigma to the bottom, apply the chain rule to sigma sub I, so we have negative 1, and this becomes the gradient of sigma sub I. Okay, now if you plug in the gradient of sigma sub I into here, and then do a bunch of algebra, you'll get a very simple expression that looks like this. And then if you plug in sigma sub I, you can have an expression in terms of sigma, x sub I, and theta, as desired. Okay. So there are a lot of, so all these expressions look pretty hairy. When you work through the algebra and try to do some simplification, you'll get out some pretty simple results. And so what you should do at home is make sure you can take the gradient and go from start to finish, knowing that your result should be pretty simple. Okay. To give a sanity check on our answer, what we can do is look at this gradient of the loss and make sure that it has the right dimensions. What should the dimensions of the gradient of the loss be? Should be a p by 1 vector, because theta itself is p by 1. So we can check that. The sigmoid applied to a dot product, so the dot product is a scalar, and the sigmoid applied to a scalar is itself a scalar, and a scalar minus a scalar is a scalar. So this whole parentheses here is a scalar, a single number. X sub I is p by 1, and so we get out the final vector is p by 1 as desired. Or really, I call it a length p vector. In this class, we don't distinguish too much between column vectors and row vectors, but in this case, I'll just say it's a length p vector. Okay, so now we can plug it into our gradient descent update rule. So here's our gradient descent update rule. And what we do is we take this expression up top and plug it in. And there it is. And that's the gradient descent update expression for stochastic gradient descent for logistic regression. Okay. So here's the update rule. And it turns out that if you take that gradient, you'll notice that there's no real way to solve for theta. And so we can't solve for theta, and so we'll use gradient descent. I'm going to give you a few tricks for helping gradient descent converge, because it's actually pretty tricky to get gradient descent to converge properly. What we'll do in the next demo is I'll start with a high learning rate, and I'll decrease that learning rate over time. We call it the learning rate decay. Okay, we decay that learning rate over time until it's small. And the idea is that when we start gradient descent, we want to take big steps. We want to learn as fast as possible. But when we're after we run gradient descent for a while, we want to decrease our step size so that we can converge on that single minimum of the loss function. Okay, the next thing we'll do is we'll clip the gradients if they get too far from 0. And this is called gradient clipping. Okay, so essentially, if our gradient is too big, we'll just make it smaller. If a gradient is too negative, we'll make it less negative. Okay? And that way we don't have really big updates for our theta values. And that helps our gradient descent converge because we'll be less likely to get some crazy theta values. Okay, now it turns out that there are lots. What's going on here? There we go. It turns out that there are a lot more tricks for gradient descent, like these ones here. So there's 2 tricks here, but in real life there are many, many tricks. And a lot of them are ad hoc or appear to be ad hoc. And the reason why they feel ad hoc, so it feels like you could have made this up. And it feels like if you made it up, you would have gotten something pretty reasonable. And it feels like kind of made up or pulled out of someone's butt. Sometimes they are. And it turns out that gradient descent theory is this very active research area. And so people, generally speaking, come up with these rules that turn out to work really well in practice. And no one really knows why until a few years later when someone actually does some theory on the gradient descent rule. A lot of the algorithms that we'll use to fit models in scikit-learn, for example, are very recent. So the Saga algorithm that I showed you before, that came out in 2014, which is only 5 years ago. Okay, so these are some pretty new algorithms, and it's a pretty active research area. And machine learning research is a pretty hot topic right now. So even algorithms that are a year old are considered pretty out of date. That's just kind of the state of research in this field. In any case, what you should know is that there probably is theory for these two, but for the very new tricks, there isn't too much theory. And people are trying to figure out why these things work. Okay, so let me show you the demo. I have here a derivation of the logistic regression update rule. I have some functions here that I'm going to skip implementing because we've implemented them before, and I do want to make sure we end on time, so here they are. But what you should do is you should take this notebook and remove all these things and make sure you can implement them yourself. Okay, they're all one-liners, so they're not too bad, hopefully. Here's a loss. It's long. I have all the algebra in here, but you can go through this on your own time. Skip all of this. All right. So you have your gradient descent. And sadly, I wanted to implement this for you, but I'm scared of making mistakes, so I'll copy and paste the answer. Here we go. Okay. What I want to show you is how we do gradient decay, the learning rate decay, as well as gradient clipping. Okay, so here's gradient descent. And I'm just going to run batch gradient descent because the code is a little bit simpler than stochastic gradient descent. If you want to implement stochastic gradient descent, I actually suggest you do that as an exercise and make sure you can get it to converge. And if you do that, you'll run into a lot of the difficulties that we have with making that gradient converge. Okay. So here we have batch gradient descent. And what we'll do here is we have this expression when we update theta. Okay, so here I compute the gradients. And then what I do is I say that my learning rate, or my alpha, is originally 5. And what I'm doing in this expression is I'm saying, as I increase the number of iterations, make the learning rate smaller. Okay, so this is alpha divided by 1 plus t over 1,000, where t is a number of iterations. And so when t is 0, this expression becomes alpha itself, or learning rate itself. When t is 1,000, then we have 1 plus 1 on the denominator of this fraction, and so we have half the learning rate that we did before. When t is 5,000, then we'll have 1/6 of the learning rate that we had before. Okay, so you can check this out yourself and verify and convince yourself that this right here decays the learning rate over time. Okay. Second thing I want to point out is this clip. Okay, so here we compute the gradient, and what we're doing here is we're saying make sure that no elements in that gradient are below this value or above this value. Okay, so if I get negative 1 million as my gradient, this right here will clip it to my default value of negative 1. If I get like 500 for my gradient, this will clip it to 1. And that just helps me avoid like really huge steps for my theta. Okay, run that. And what I have here is a data set on breast cancer. And I believe these are mammograms, scans. And what we have here is an image of a scan as well as a column saying 1, if that scan can like show a malignant tumor or not. Okay, so malignant tumors are bad news, and what we like to do is be able to detect them more accurately. Okay, so what we do here is someone has gone through for the images and recorded down a lot of different attributes, and what we're going to do is take the attributes and use it to predict the malignant column. Okay. Here we go. If I describe this table, I can get a summary of the different columns. So here's the mean radius, mean texture. It looks like we have 37% malignant in our data set. Okay, and what I'll do here is split my data into a training set and a testing set. I will plot the radius of that tumor against whether that tumor was malignant or not. So it looks like bigger tumors are worse. All right. And as yesterday, what I can do is bin the x values and then take the average y value within each bin. And here we see what looks to us like a sigmoid curve. That should be an indicator that maybe it's a good idea to use logistic regression. Okay. So what I want to do here is I only want to take the bias column as well as the mean radius column to predict y. So here I'll have x train, y train, take my training set, take the features out of the training set, take my y, get the values. Darn, you're right. Thank you. Got that? Okay, and what I'll do here is I'll fit the scikit-learn model, which uses like an advanced gradient descent solver. It didn't converge. I think what I have to do is say, okay, so when you see this, what you should do is, if it says max iter was reached, what you should do is like look in the signature of the function here, and here it says I'm going to stop after 100 iterations. And sometimes you have to increase the number of iterations because it takes some algorithms longer to converge. So I'm going to increase the iterations to 1,000. Let's try it again. Throw a comma. Didn't converge again. Okay, so I'm going to try it. I'm going to increase the iterations, and now it's happy it converged. Okay. Here we go. And I can take the scikit-learn model and plot the model against my binned averages, and it looks like it fits the data pretty well. And now what I can do is run my homegrown logistic regression function and see if I get the same thing as scikit-learn. Okay, so here we have, I'm going to time this cell because it's going to take a little bit of time to run. Theta equals logistic regression on x train and y train. And I'm going to print my theta at the end. Okay, so let's cross our fingers. So I have here, it prints out the theta value, the gradient, and the loss, the average loss every 50,000 iterations. It turns out that when you write your own gradient descent, it takes a lot longer than the ones that are built in. because the ones that are built in have a lot of optimizations. Okay, but there's a whole field of research dedicated to like making these algorithms run fast, because a few years ago, 1 million data points was like unthinkable. It was like unbelievably big, and now 1 million data points I can do on my laptop, and now we're like working in data sets of like trillions of data points, and now and sooner or later, I'm pretty sure those will become small data to us one day. Okay, so there's a whole field out there like looking at ways of making these things faster, and usually the thing you don't want to do is write your own gradient descent algorithm every time. But it is important to know how it works, because you do want to be able to tune it. Okay, so we see here that we got negative 14.9 and 1.01. It's a little bit different than the model's predictions, but it's pretty close. And if I plot the predictions of my homegrown logistic regression model, here's theta 0 plus radii times my theta 1, I see that both curves fit the data pretty well. Okay, I can also take a look at the predictions of my scikit-learn model. I'm going to multiply by my coefficients, like so. Look at the empirical risk on my training set, my predictions, and the log loss. That's my empirical risk. If I look at my model's predictions, I can change these two variables. Our loss is a little bit lower. Turned out that we did pretty well. And the reason why we did a little bit better is because scikit-learn has like regularization built into the classifier, and so it did a little bit of regularization. Okay, now what we can do is check our performance on our test set, and looks like we're running out of time here, so I'm going to skip to my answers. Scroll down here. All right, here we go. So I look at my test set, and I see that there were 56 malignant tumors in my test set. I'll define my area under the curve metric and use that to check the performance on the test set and the training set. Okay, so darn, this is a different notebook, so I have like different things. Okay, so here we go. I'm going to take this, copy it, paste it. Does that work? Copy, paste. All right. Okay. I have to import this. See that? Okay. So it looks like that. It looks like our model actually does better on our test set than our training set. That happens sometimes if our test sets are pretty small. In this case, our test set is only 140 points, so I would suspect some variation here in this area under the curve. We can also compare a model that uses all the features instead of just one feature. So here I'm only using the mean radius of that tumor, but you can imagine that a model might use all the columns in our data set. So I can drop the malignant column, and this is all the rest of the features. And then I can write, let's see here, my model is this code right here, which is just the same code that I had before. Hit that, let that run. My homegrown gradient descent takes a long time to run on this, so I won't bore you with that. But I can again check the accuracy here. It looks like again, I'm doing a little bit better on my test set than my training set. My area in the curve here is pretty good. And I would interpret this to mean that using the features for the scan seems to do a pretty good job, or gives us pretty good signal at detecting whether a tumor is malignant or not. Okay, so there are lots of metrics. Don't memorize them, because you can have a cheat sheet on the exam and you'll be able to reference things in real life. But you should know their names so you can look them up when you need to. You should know how to draw an ROC curve, know how to compute the area under the curve and know what it means. And you should practice that derivation for gradient descent until it becomes second nature to you. That's all I got for today, so I'll see you tomorrow.